Myself, Professor Ritesh Mahajan from Marathwada Mitra Mandal Institute of Technology, Lohgaon, Pune. So, I am here to discuss the unit number 4, Dynamic of Robot and its Motion Planning and Control. So, in this lecture number 1, I am going to discuss the dynamics of robot. So, in the earlier unit, that is unit number 3, we have learned the concept of kinematics of robot. And in the kinematics of robot, we considered the different types of kinematic motions, link motions of the your robot manipulator. So here robot dynamic. Robot dynamic means what? To study the relative motion between the applied forces and the torque of the robot manipulator. Means in the robot kinematic we learn the different types of movement, joint movement of your robot manipulator. But here will the aim of the study of the robot dynamic is to determine the joint torque and the forces. So like the concept we learn in the robot kinematic, here also we have the concept that forward robot dynamic and inverse robot dynamic, or you can say direct dynamic and indirect dynamic. So the direct model is nothing but what? From the given joint force torque, resultant motion of the robot manipulator that can be calculated, that is called as a direct model, or you can say forward dynamics. Means from the applied force or the torque at the joint of the robot manipulator, we are going to calculate the different angle, like say deflection, angular velocity and angular acceleration for that particular manipulator. That is nothing but we can call as a forward dynamic. And inverse dynamic means from the joint acceleration, velocities and position, we are going to find out the forces and the torque at that particular joint. So in this particular study, we are going to focus the inverse dynamic. So there are the different methods to find out the joint acceleration, to find out the forces and torque from the acceleration, velocity and the positions of the joints that may be given. So in this figure we will getting the, as I explained in the forward dynamic, suppose you know the joints and forces at the torque. So here T I to Tj, so starting from T1 to up to the Tj, and if you consider, so in this figure we will getting the, as I explained in the forward dynamic, suppose you know the joints and forces at the torque. So here Ti to Tj, so starting from T1 to up to the Tj, and if you consider the force F1 up to the Fk, so simply these are the input. That means here in forward dynamic the inputs are nothing but the force or the torque at the joint, and from that we are going to determine the displacement, position, angular deflection of that particular robot manipulator, angular velocity and the angular acceleration. So that is nothing but the forward dynamic. In inverse dynamic we have the positions, angular velocity and the angular acceleration, which is shown here q1, q1 dot and q1 double dot, that are given, and we can compute or we can calculate the torque and the force for that particular robot manipulator. So that is the inverse dynamic. Now approach for dynamic modeling of the robot manipulator. So as I said, to compute the torque or the force from the different position, angular velocity, acceleration given for the particular joint of the robot, in case of inverse dynamic we can use this two approach. The first one is nothing but the Euler-Lagrange's approach, and second one nothing but the Newton-Euler approach. Now what is the Euler-Lagrange's approach? So that is the energy based approach, in which we'll simply take the difference between the kinetic and the potential energy of the body in motion. So here in the next slide we are going to discuss in detail for the kinetic energy and the potential energy of the rigid body in motion. So simply, when the Euler-Lagrangian approach is based on the energy difference, while the Newton-Euler approach, it is based on the force and the momentum of your manipulator. So let's start with the Newton-Euler approach first. So in the Newton-Euler approach, as it is based on the force and the momentum of the manipulator, so the relations between the joint position, velocity and acceleration of the manipulator and the torque forces applied by the actuator and the external forces which cause the motion, that is given by the Newton's second law of motion, that is force is equal to mass into acceleration. While the angular acceleration and the torque that need to be applied at the different joint of the manipulator, that angular acceleration, because of that angular acceleration, the whatever the inertia, considering the inertia, the torque is developed, and that torque is given by torque is equal to moment of inertia multiplied by the alpha. So these two equations will define the Newton-Euler formulation. Next one, Euler-Lagrange's approach. So as I discussed in the last slide, that Euler-Lagrange's approach is nothing but the simply a difference between the energies like potential energy and the kinetic energy. So let us consider if here Q1, Q2, Qn and Q1 dot, Q2 dot up to Qn dot are the joint position and the velocity variable in case of generalized coordinate system for the particular type of robot manipulator. Then its kinetic energy is given by K is equal to 1 of mv square, where here V can be determined in case of displacement, so that is the dx by dt, that is nothing but a derivative of here we are defining the displacement of the position by q. So what we can consider, velocity is function of q dot. The potential energy is given by mg into h, so it is the function of q. Now here q is considered, as I said, it is the deflection or the displacement or the position. So simply, according to the expression of the Euler-Lagrangian formulation, or according to the principle, it is a difference between kinetic and potential energy. I can write the equation that Lagrangian equal to K minus P, where K and P are the kinetic and potential energy of your system respectively. Next one, Euler-Lagrange's approach. So as I discussed, now we have to following generalized equation in the second order differential equation for linear one. So that may be defined as force for translational motion is d of dx in bracket delta L by delta xi minus delta L upon delta xi. This is for the translational system, where torque for the particular body or the particular manipulator is d by dt of delta L by delta theta dot I minus delta L by delta theta I, where here for translational system F is the summation of all external forces for linear motion, torque Ti is the summation of all rotational torque for the rotary motion. Here, as I am saying, Qi, or you can say that is the position vector, so that maybe you can call x for linear motion, and theta, angle theta is nothing but q in case of rotary motion. So simply by these expression will define the Euler-Lagrangian formulation. Now that Euler-Lagrangian formulation that I am explaining with the help of this example. So whatever we define, that Euler-Lagrangian formulation is the difference between the kinetic and the potential energy, and from that we have to determine the force or the torque at the joint of your robot manipulator. So that can be explained with the help of here single degree of freedom system. Consider the simple pendulum